All right, let's talk about something we use every day. Words like work, energy, and power. But what you might not know is that in physics, these words have a secret meaning, a really specific language that describes how everything in the universe moves. And trust me, once you learn this language, you'll never look at the world the same way again.
So, let's kick things off with a classic brain teaser. You've got this weightlifter, right? He's holding a massive barbell over his head. He's sweating, his muscles are shaking, he's clearly putting in a ton of effort. But here's the question, is he actually doing any work on that barbell? In the world of physics, the answer is a big, fat no. And figuring out why is the key to this whole explainer.
So here's the deal. The whole confusion comes from the fact that we're dealing with two totally different definitions. In everyday life, work is anything that makes you tired, studying, carrying groceries, you name it. But physics is way more specific. For a physicist, work only happens when a force succeeds in moving something. If there's no movement, there's no work, period.
To get just a little more precise, for work to happen, you need a three-part checklist. First, you need a force. Check. Second, you need displacement. The object has to physically move from one place to another. Check. And third, and this is the real kicker, that force has to have at least some component that's pointing in the same direction as the movement. If you're missing any one of those, you've got zero work.
This brings us right back to our weightlifter. He's applying a huge upward force, but the barbell's displacement is zero, so no work. It's the same reason you can push against a brick wall all day and not do any work. The wall isn't going anywhere. But the example that really blows my mind is when the force is perpendicular to the motion. Think about the moon orbiting the Earth. Gravity is constantly pulling the moon in, but the moon is moving sideways. Because that force and the direction of motion are at a perfect 90-degree angle, gravity does absolutely zero work on the moon. Crazy, right? Okay, so we've nailed down that work is the physical act of a force causing something to move. Great, but what's the actual result? I mean, how do we put a number on the change in motion that the work actually creates?
And the answer to that question is kinetic energy. The best way to think about it is as the currency of motion. Any object that has mass and is moving has some amount of this energy. The heavier it is, or the faster it's going, the more kinetic energy it has. That's why a moving car has so much energy that you need really powerful brakes to get rid of it and bring the car to a stop.
So now we have our two main players on the stage. We've got work, which is the action, the force pushing over a distance, and we've got kinetic energy, which is the result, the energy of that motion. So what's the fundamental connection? What's the simple, beautiful rule that ties them together? This is really the heart of it all.
And here it is, the work-energy theorem. It's so elegant, it's just awesome. It says that the net amount of work you do on an object is exactly equal to the change in its kinetic energy. It's a perfect transaction. If you do 100 joules of work to push a box, you have given that box exactly 100 joules of new kinetic energy. Simple as that.
But wait a minute, that brings up a new puzzle. What happens when you do work on something, but it doesn't start moving? At least, not right away. Imagine pulling back the string on a bow and arrow. You're applying a force over a distance, so you're definitely doing work. But the arrow isn't flying yet. So, where did that work just go?
It gets stored. It's converted into what we call potential energy. Energy that's saved up because of an object's position or its configuration. That stretched bowstring is just loaded with potential energy. But here's the catch, and it's a big one. This whole idea of storing work and then getting it back later only works for a very special class of forces called conservative forces.
You know, the best way to think about it is like a bank account for energy. Conservative forces, like gravity, are like a perfect bank. The work you do lifting a ball up gets stored as potential energy, and you can withdraw all of it when you let the ball drop. But non-conservative forces, like friction, they're like a transaction fee. The work you do against friction gets turned into heat, and that energy is basically lost from your mechanical system. You can't get it back.
Let's actually watch this in action. Here we've got a ball being dropped, and the only force we care about is gravity, a conservative force. So look here. At the very top, it's all potential energy, no motion. As it falls, watch what happens. The potential energy goes down, but the kinetic energy goes up by the exact same amount. And that last column, the total energy, it stays perfectly, completely constant the entire way down. The energy just changes its form from potential to kinetic.
And this all leads us to one of the most important, most powerful laws in all of physics, the principle of conservation of mechanical energy. It basically says that as long as you're only dealing with those perfect bank account conservative forces, the total mechanical energy of a system will never, ever change. It is always conserved.
Of course, in the real world, that's not how it works, right? We've almost always got non-conservative forces hanging around. Friction, air resistance. A ball rolling across the floor doesn't roll forever. It stops. So what happens to our beautiful law of conservation then? Does it just break?
No, it doesn't break. It just gets a really elegant update. It turns out the change in a system's total mechanical energy is exactly equal to the work done by those non-conservative forces like friction. So friction doesn't destroy energy, it just moves it out of the mechanical system, usually as heat. And this finally brings us to power. Power is all about the rate of energy transfer. It tells you how fast you're doing work. A powerful engine can do a lot of work in a very short amount of time. And powerful brakes can turn a lot of kinetic energy into heat very, very quickly.
Which leaves us with one final big idea to chew on. We've seen that mechanical energy can be lost from a system because of friction. But one of the unbreakable laws of the universe is that total energy is always conserved. So when friction stops a sliding block, where did all that kinetic energy actually go? It didn't just disappear, it simply changed form. A little reminder that in our universe, energy is the ultimate shapeshifter.